Hello everyone, my name is Ishan Sharma. Welcome to our time series analysis project. In this project, we will delve into the fascinating world of analyzing time based data to gain insights. We will explore trends, patterns, and behaviors over time and uncovering valuable information from our data set. So, let's start. Okay. Today we have Tesla stock price data, which you guys can see here, and we will use time series ARIMA model and SARIMA model to predict the closing values of the stock price. Okay. So in this project, we will do five things. One is data ingestion, okay, and second thing is exploratory data analysis. Third thing is pre-processing of the data. Fourth thing is model building, and fifth thing is model evaluation. So first of all, for data ingestion, we will import the libraries as you can see here. Pandas is for converting the data into data frame. NumPy is for numerical calculations and stuff. Matplotlib is for plot, and this other things if we need this OS and SYS. And now in this data variable, we are storing our CSV file which is named as TSLA. Now we will be seeing the first five rows of our data. Okay. Now we are choosing date and the closing price of it only. We are doing this because here we will be analyzing the univariate time series only. Okay, so that's why in the stock underscore data, we chose only two columns, data and close. Okay, so yes. Now, since we chose only two features, now we will be seeing the first seven rows of the data, which has the index, the date, and the closing price of the stock. Okay, this is the data of 3 years of Tesla stock price, starting from 2019 to 2022. Okay, now we will see the info of this stock underscore data. So here you can see this data is being considered as an object, and this close is considered as a float type. We don't have any problem with the close, but we have a problem with the date because going forward we will be using libraries in which we want date as data type as date time 64. Okay, so because of that we are changing the date into pd to date time. Okay, data, we are changing the data type of date. Okay, so here we have changed this code we have used for it, and now we are again checking the info of the data. So this date has become date time, this data type. Okay, now we are just seeing the first two rows of our data. So here it is. Now uh, in that stock underscore data variable, we are just removing the index and removing it with the date. Okay, because going forward we will be using it. Going forward, the libraries need data as date as index. Okay, yeah. So here we have like why we are converting date column as index column, because we can easily retrieve the data if we do that, and visualization becomes simpler. And last but not the least, the libraries which we will be using going forward, especially this SkyPy and stats model, requires date as index. Okay, so now again we are just seeing the first five rows of the data. Now we are doing the exploratory data analysis. Okay, so yeah, in the exploratory data analysis, we will see the summary statistics, which is like we will compute the summary, that is the mean, median, mode, standard deviation, to get the overview of the data. We will visualize the time series data. We will plot the time series, plot the rolling mean, rolling standard deviation of the time series data, We will decompose the time series data, check for trend, seasonality, noise, and plot the decomposed components to get a better understanding of the time series data. Then we will check the stationarity. If the if the mean is same throughout, then you can say it is stationary. Also, we can use this augmented Dicker-Fuller test to see whether our data is stationary or not. Then we will check the autocorrelation. We will plot the autocorrelation function and partial autocorrelation function to identify the order of the ARIMA model. Then using box plot, we will detect the outliers, and then again we will check for autocorrelation and partial autocorrelation to identify the order of the ARIMA model. Okay, so here we have used this dot describe function, and we have got like count. So there are 758 rows and mean is 785. This 25% means like there is 25% of the data is less than this 112 number. Okay, and similarly 75% of the data that is third quartile is less than 762. Now we will plot the stock underscore data dot close, the closing value. We will just plot that. So this is the graph. Like as the time is progressing, the closing price is increasing. Similarly, like here you can see we have just used this plot. Here we will use that histogram. So nothing else. We have just used the histogram here. And now here we are plotting the closing price. Okay, here what we are doing is we are just using, we are just giving it a heading. We are making it more fancy. Okay, so like you can see like here we are giving it a title using the Python function, and this plt dot figure, this figure size 18 comma 8, decide the dimension of the graph, and plot the dot grid indicates the lines, and this font size shows the size of like this 1200 and 1000. Okay, something like that. And this label is to label the x-axis, y-axis. So here also you can see as the time is progressing, the closing price is increasing, then going a little bit down. Okay. Now here we are just again plotting the histogram, but here we are just making it more fancy. We are just giving it a title, and so that is better to understand. Now we are just again, initially we have used that plot, then we have used histogram, now we are using this distribution. Okay, so yeah, so here is the graph of this. Now we are using this roll mean. Roll mean means it's a moving average. So what rolling mean does is it find out the mean taking average data of the time series within k period. So in a certain period it finds out finds out the mean. So here I have chosen 48. So after 48 days it will find out the mean. Here like in roll standard deviation, it will find out the standard deviation after 48 days. Now we are just plotting the stock underscore data dot close graph and the roll mean and the roll standard deviation. Here you can see the roll mean is not smooth. So since it is not smooth, we can conclude like our time series data is not stationary. Also with the help of the ADA Fuller test we can do that. Okay, so here comes this ADA Fuller test. So this is the syntax of it. Okay, here the null hypothesis in this ADA Fuller test is the data is not stationary. Okay, and the alternative hypothesis is the data is stationary. And if the p value is less than 0.05, then we can accept the alternative hypothesis. Lekin here the p value is greater than 0.05. This means we have to accept the null hypothesis, and which says that the data is not stationary. Okay, so from the test also, this p value, we can say the data is not stationary. Okay, now again we are using this test for stationarity. So this code is not very difficult to understand. You can just search it on Google. It is basically exists to make the graph more fancy. For example, this original rolling mean rolling STD comes from the legend plot, the PLT dot legend. Okay, this rolling mean and standard deviation comes from this title. Okay, and this plt dot plot, this plot, one plot plots the original data, the second plot plots the rolling mean, and the third plots the rolling standard deviation. And as we have said earlier, 48 days is the gap. We have said we can take different gaps, there is no issue. Okay, as we increase the number of days, the graph becomes smoother and smoother, so it's like that. So here you can see the rolling mean is not, exactly smooth, or I should say it is still varying. Here also you can say na, p value is greater than 0.05. This means our data is not stationary. So we will decompose the data, and we will do that from this library statsmodel.tsa.seasonal. So here seasonal means something that has a frequent repetition, like daily or weekly. So like for example, we have a ice cream season. Okay, so it's like that. So since we have saved it the variable as result, so it's result dot seasonal, and here it is the closing price. Okay, it is basically the variation. Now we will plot the figure. Okay, and as you can see, like there are in time series there are four things like trend, season, cycle, and noise. So this one is the original data, this one is the trend. Trend can be up, down, flat. Here it is up. And seasonal, as I said, it is frequent repetition. And this recede. So yeah, now after that, uh, again using the same library, we are here changing the model. We are changing into it to multiplicative. Here the model was additive. Okay, so we will again plot the graph. This is the original graph. This is the trend, and this is the seasonality, and this is the receipt. Okay, now we will import the seaborn library as SNS. We will do that to make the box plot, and we make the box plot to check whether there is an outlier or not. So from this box plot we can see that there isn't outlier. So yes, again we are making the box plot, this time more fancy. So we are just giving it a title. It is basically same. So nothing much. Now we are just making the graph of autocorrelation. Okay, and partial autocorrelation, and these libraries are used for it. Okay, so here you can see the autocorrelation uh, is almost same. This also means that our data is not stationary. Okay, and in what is partial autocorrelation? So, okay, let me just first say what is autocorrelation. So, it is how similar our values within a given time series uh, and previous value. And this PA, partial autocorrelation, is when intermediary effects are removed. It is same as autocorrelation. Now we will do the pre-processing of the data. Okay, so yeah. Pre-processing means first we will fill the missing values. Here it is not required. Then we will convert the data into stationary time series. Then if necessary, we will normalize the data. Here it is not required. Then we will split the data into train and test, and then we will clean the data by removing the outlier. But since there isn't any outlier, we have seen from the box plot, so we will not do that. Okay. So we will first convert the data into stationary time series, and for that we will be using this differencing. Okay. So let me tell you what is differencing. Differencing is transformation of series into a new time series, which used to reduce the series dependence on time and stabilize the mean of the time series. So trend and seasonality are reduced during transformation. Okay. So we will be using this differencing technique. Okay. So here we have chose two. Okay. So because of that, we have two NaN here. Okay. Now since we have got NaN, so we are going to drop those rows. So here we have dropped them. Okay. Now after that we will check for the stationarity. Okay. So here you can see the mean is very close to a straight line. So here we can say that our time series data has become stationary. Here you can see from the p-value as well, the value is less than 0.05, which means we need to reject the alternative hypothesis, which is that our data is stationary. Now, in the fig variable, we will plot these figures, the autocorrelation figure and the partial autocorrelation figure. So from the graph also, you can see there isn't any there isn't a lot of difference. So this autocorrelation also states that our data is stationary. Similarly, the partial autocorrelation states the same. Now this df underscore close. So by this 0 to minus 60, I mean like number it. For example, 0 here, 1 here, 2 here, 3 here, 4 here, and similarly the length is 697. So 697 here, 696 here. Okay, so this is like numbering it in simple order. And when you order it like in minus, so you will order like this, like -1 here, -2 here, -3 here, -4 here. Okay, so from 0, that means from 0 here to minus 60, somewhere between here. Okay, we are just breaking the data. Okay, so here we are breaking the remaining data from -60, which is somewhere like you can number it. For example, -1 here, -2 here, -3 here, somewhere here, -60 to till the end. Okay. Now we are doing this because we are splitting the data into train and test. Okay. So in the train, we are just putting from 0 to -60, which is a lot of data. I think it is somewhere like 70% of the data. And in the test underscore data, we are putting the remaining 30%. Now we are plotting the figure. We are just writing the dimension 18, 8. Now we are just labeling dates on the x-axis and closing price on the y-axis. Now font size is 15, that is it can be easily understood. We are using this plt.plot. We are placing the train data and the test data. This green line represent train data and this blue line represent test data. So it is like from 0 to -60 it is trained, and from -60 to till the end it is the test data. Okay. Now we will do the model building. Okay. So for the model building, first we will import the required libraries, which is this stats model.api. Also, we will import this ARIMA mean square error, mean absolute error. Our goal is to minimize the mean square error. And yeah, so let's get started. In the history variable, we will store the train underscore data, and in the model variable, we will use this ARIMA to check whether our model is good or not. So here we have chosen order as 1 comma 1 comma 1. Okay, so here P is the lag order, which is the number of lag observation. D is degree of differencing, number of items that the raw observations are differenced, and Q is the order of moving average, the size of MA window. Okay, moving average window. Okay, so here we are just fitting the model, and now we are checking the summary of it. So yes, here the ARIMA order we chose is like 1 comma 1 comma 1. So here it is. Here it is the value of coefficients. Okay, this is an inbuilt function, so you can just use it to find these values. Now we will be doing the forecasting. So we are using this forecasting function. So we have forecasted one value, and then we have found out the test data. Okay, now we are finding the mean square error between this data and the forecasted value, which is this 81 point this. Now using this numpy, we are finding the square root of mean square error, which is this 9.05. Now what we are doing is, initially we have used 1 comma 1 comma 1 as the value of PDQ, but here we are just considering all the values. So we are ranging P from 0 to 3, D from 0 to 3, and Q from 0 to 3. So here we have used for loop 3 times to write down all the possible values of this PDQ. Okay. Now we will use this train ARIMA model. Okay, and to prepare the training data set and make the prediction list. So this command will make the prediction list, and here we are also appending things like this y hat, the forecast thing, and the prediction list. We are just appending that, and we are appending this YT as well as the history. History is our training data. Okay, and now here it is, RMSE is root mean square error. Okay, now we will evaluate the model. Okay, and in that we will find out these values PDQ. Okay, our goal is to just reduce the RMSE as much as possible. Okay, so for that we have evaluated like the model on each and every order, like from 000 till 222. Okay, and if you can see, the RMSC is minimum when it is 1 comma 2 comma 2. So that is the best ARIMA, best order when the value of P is 1, uh, D is 2, and Q is 2. Yeah, so now here again we are using this training data, and here we are writing this alpha value, which is 0.05. So this means the confidence interval is 95%. Had we not given this alpha value, then it would have by default taken the confidence interval value to be 90%. Okay, so it's like that. Now we are seeing the test data. Okay, from -60 till end. Now the predictions we have made using the training data. So here we are just making the graph of true test close value and prediction on the test data. So we are use this command to plot the graphs. So basically this is simple Python. So this is the graph. Prediction is more of a linear, whereas the true test close value is varying. Now, in the FC underscore series, we are just converting it into a series. Okay, that's it. Yeah, the index, we are giving it an index, and here you can see the series. Now, we are plotting the graph of forecast versus actual on test data. So we have test data from -60 to 0, and we have forecasted the data based upon from 0 to -60. Okay, so this blue line is from 0 to -60. This is uh, from -60 till the end, and this is our forecast. Our forecast is more of linear. Okay. Now here we are making this graph for the confidence interval. So here you can see this is the 95% confidence interval graph. Okay, and it is like written over here, it is written like plus 60, so it is finding out the next 60 values, predicting the next 60 values. This is for the forecast and this is for the close. Now we will evaluate the parameters, and for that we will be using this ARIMA model. uh, Sarima here, S stands for seasonality, and ARIMA is like auto regressive integrated moving average. Okay, so here RMSE of the model is 57.89. Okay, now in the end we will be making the forecast versus actual graph. So as you can see from the graph, this is like simple code for title, this is for plots, this is for prediction plot, this is for close plot, and this is plot dot legend for these things like these lines. Here you can see the prediction, the forecast and actual is not varying a lot. So our forecast is very near to good. So yeah, so that's it from my end. In the conclusion I want to say, our time series analysis on Tesla stock aim to predict future prices based on historical data. Through thorough analysis of patterns and trends, we have gained insights into potential future movements. Keep in mind that predicting stock prices involves uncertainties, and our findings are not guarantees. Stay informed and remember that market can be unpredictable. Thanks for watching till the end. If you like the video, please subscribe the channel and like the video and share it with your friends. Thank you so much. Bye guys.